Bom dia. Thank you very much for inviting me. I would like to thank the organizers, Dr. Patricia Brandt, because it's a pleasure to be here. I come from Miami. This first slide is a picture of the Miami project to cure paralysis. This is home. The building was built some years ago, mainly thanks to donations done to the Miami project. It's called the Lois Pope Life Center, and is the house of the Miami project. I am a physician from Ecuador. I graduated in 2008. By the time that I graduated med school, I already knew that I wanted to do research. And so I went to Miami, to the Miami project, and I started doing animal research back then. And I stayed in the Miami project for the first 8 years, working on animal models of spinal cord injury. The first project I had in my hands was a primate project of spinal cord injury, where we will generate an injury that creates a deficit in the hand motion. And later I was linked to a study that was meant to create a translation of Schwann cells transplanted in the spinal cord to get approval from FDA. It was an IND application to transplant the Schwann cells into humans. This came to reality several years ago, and the first clinical trials have been started. We started transplanting Schwann cells, autologous Schwann cells, into the spinal cord of patients with thoracic injuries. And we already finished the first trial. Now the state of that is a chronic study with cervical injuries. And by the time that we came to that, I was not working so much with the animal models anymore. I started, let's call it the third phase into my research, which was related to electrophysiology, to determine if the Schwann cells were actually doing or having an effect on the motor system. So the talk that I brought to you today has nothing to do with the Schwann cells or the transplantation in the spinal cord injury, but mainly to the motor control. So the title of my talk is Neuroplasticity After Spinal Cord Injury. I'm currently working in a human motor control laboratory in the Department of Neurological Surgery at the Miami Project. So I wanted to bring some of the current work we are doing now in the laboratory. The first part I would like to talk about is neuromodulation, and this is the main part or component of my talk. Then I'll show you some robotic training that we do, and also body-machine interface, as we call it. So starting with neuromodulation. This is the work done by Dr. Karen Bunday in 2012. This was published with Dr. Monica Perez, which is the principal investigator I work with currently. It's called Timingdependent plasticity in the corticospinal pathway. This kind of work had been published before by Taylor and Martin in 2009 in people without injury. And then Dr. Bunday and Dr. Perez were the first trying this kind of protocols in humans with spinal cord injury. So in order for me to build up, because I know not everyone is going to be familiar with this kind of technique, I'm going to start by the basics, which is the stimulation of the central nervous system. So because we're interested in the motor control, we have a technique in which we stimulate the motor cortex of a person. This kind of technique is old. It was started more than 30 years ago by Merton and Morton, where they were stimulating electrically the motor cortex of people. And their observation was that when you put current near to the head of a person, the limb will move, the arm will jump. And their interpretation of this was that there is a connection that you can evoke, and the homunculus idea came from those studies. That was expanded into primates and later on more into humans. What we do is transcranial magnetic stimulation, or we call it TMS. TMS is a technique where you put an electromagnetic coil nearby the motor cortex of a person, and the electromagnetic coil generates a strong but focalized field, an electromagnetic field that excites neurons that are nearby the cortex. These neurons, if you allocate the coil correctly, can depolarize muscles in the hand. The other part of this is electromyography, which probably you're more familiar with. To collect the electrical muscle activity, you can just use surface electrodes. It can be done with needles too, but surface electrodes suffice. And the changes in the electrical activity of the muscle give a good idea of the connections that are evoked or elicited from stimulating the brain and going across the spinal cord. So this is a very desirable tool to evaluate the motor system after spinal cord injury. As I mentioned before, when I started working in animal models, part of my work was to translate or to adapt a little bit this to the pig model, which have not been very well studied into this motor system with electrophysiology. And I realized the importance that there is in this kind of techniques to actually prove that some therapies like stem cell transplantation do have an effect other than just the behavioral effect that you can see. So let me go back now to spike time-independent plasticity. The concept here is to have an action over these neurons. This is representing here 4 alpha motor neurons in the anterior horn of the spinal cord. They do connect or receive direct connections, monosynaptic connections from the cortex. And this is a particular feature of the human corticospinal tract. Just high hierarchy primates do have these kind of connections. Other mammals have similar connections, but those are not monosynaptic. And this is an important difference when you want to interpret results coming from rodent models or pig model. Because these have been linked, this direct connection has been linked to the dexterity of the human hand. In this protocol, the idea is to give 2 stimulus to these neurons. And by generating a sequence of a double pulse stimulation that comes to this neuron, the neuron gets into a plastic state. This means that the connections of the neurons get reinforced and they changed. And this is the principle of short-term learning and long-term learning. And in the motor system, of course, and it requires repetition. So what we do is we send a signal from the brain by stimulating the motor cortex. The signal comes down and it has to match or meet with another signal that we do in the peripheral nerve. We stimulate the peripheral nerve, in this case the median nerve in the hand. The stimulus goes back up through the same pathway that is gonna come back down, and it meets with the other signal in the alpha motor neurons. This concept is very important and is the center of the spike time independent plasticity. I'm representing here a segment at C8 and T1, so below the injury. And the purpose is that after injury, some of these connections have been disrupted and just some are spared or remain. And we believe that people with spinal cord injury in most cases, do have some of these spare connections available, but they are not functional. So by training these connections, we believe that people can recover. And this protocol has that as a goal. The hypothesis was that arrival of corticospinal bodies prior to motor neuronal discharge at residual corticospinal synapses will enhance voluntary motor output in humans with spinal cord injury, with chronic spinal cord injury, and this is at the cervical level. So here there is a schematic of the system. Again, the stimulation comes to the brain, to the motor cortex. Then it has to travel down to the spinal cord and reach the synapse. And then from the synapse it goes to the muscle, where we monitor using electromyography. Here a representation of muscle in the hand. This is the first dorsal interosseous. It's a muscle that allows movement of the index finger in abduction. It's a very good and consistent muscle to get data from. So the first part to understand is that we need to do calculations and estimations of how much time it takes to reach from the cortex to these neurons. Because if we want to bombard these neurons with 2 pulses to make the stimulation to come here, we need to time it precisely. And the way we do this is we get first an idea of how much it takes to reach from the cortex to the muscle. And that is called the motor evoked potential. Motor evoked potential is a change in the muscle that we can monitor and quantify. It's visualized as a single tweak in the muscle. But if you put electrodes there, you can see that this tweak has actually a latency, which is the time that it takes to reach from the stimulation to where the response is, and also an amplitude, which depends a lot on the intensity that you use in the cortex. And also, it tells you how much of the pathway is still preserved. So here I'm showing 2 cases. The upper trace is a average of 20 trials in a normal person or a person without spinal cord injury. And the latency, the time it takes to reach from the cortex to the muscle, is around 22 milliseconds. And that is considered normal for people without spinal cord injury. Now, after spinal cord injury, you can see down in this lower trace, also 20 repetitions averaged, that the latency time is prolonged. In this case, up to 27.6 milliseconds. So about 4 milliseconds later, because of the injury it has to go through, and it's slower. So in the next slide, I'm showing the second component to time, or to find out the time. So now what we're doing is we stimulate nearby the cervical area. And the purpose of this stimulation is to get right to the segment, for example at C8, T1, and time how much it takes to go from the segment to the muscle. Again, in this case, what you're seeing here is the average of 20 repetitions, and the time that it takes in a person without spinal cord injury in the control is 15.9, almost 16 milliseconds, while in the case of spinal cord injury subjects, it's a little prolonged to 18. And this is very important because we do a third measurement, now stimulating still the peripheral nerve, but closer to the muscle. This stimulation comes from the median nerve in the wrist, as I showed you in the previous slide. And it goes in both ways, up back to the spinal cord, but also down to the muscle. And when it comes down to the muscle, we can monitor that, and we call that the M wave. And if you stimulate strongly the nerve with sufficient current, this gives a very good signal, an idea, a quantitative idea of how much of this muscle is responding to or is connected to the nerve. And then you can use these to subtract the amplitude from the stimulation that came from the brain, telling you a percentage or how much of this total stimulation is coming through. That's also a very good and useful method. But what we do mainly here is, again, measure the latency or the time that it takes from the stimulation to the response. And then we add this number to this other number, and we subtract that total number from the main latency. And that gives us a measurement of central conduction time. That's how it's called. Central conduction time, therefore, will be the time that it takes to reach the spinal cord from the cortex. So now, using this technique and this timing, we know how much time we need to use for the interpulse interval to reach here in the alpha motor neuron. And let me show you in the next slide, it's a little bit clearer. So here I have three examples where were analyzed in this study by Dr. Bundai. First, they used a facilitatory state where the stimulus coming from the brain will reach the spinal cord first, and then the stimulus coming from the peripheral nerve will reach the alpha motor neurons. So in this case, we call it positive 1.5 milliseconds, but actually, because this is coming earlier, it should be a negative time in comparison to the other two states. The second state is the inhibition. So here, this is our control. So the inhibitory protocol reaches first from the cortex, the alpha motor neuron, while the periphery comes, it comes first from the periphery and then second from the motor cortex. And we put an interval in between these two pulses of 15 milliseconds. And we observe inhibition. I'll show you what I mean by that. And then this is the third state with a neutral or a non-responsive state. This is also a control, where the first stimulus comes from the periphery and second stimulus from the spinal cord, and the time in between these two stimulus is 5 milliseconds. So as you can see, we can control very well the time we have very fine control of the time in between one stimulus and the other. And we can build up on tests to see which ones are more effective. And once you figure out if the times are giving you positive or negative results or inhibitory results, you build up a repetition. And in this case, the protocol carries 100 per pulses, the 0.1 hertz, that takes more or less 17 minutes. So if a person with a spinal cord injury comes to us and we apply this protocol, they will do sometimes a combination of training with this kind of a stimulation for 17 minutes, and then we evaluate the changes that it provokes in the central nervous system, in the corticospinal tract. So the first concept that is coming out of this is that excitatory and inhibitory changes in motor evoked responses mimic reversible spike time independent plasticity that have been reported before in animals. This is the first case, the facilitatory protocol, where you can see the control in the baseline and the subject with a spinal cord injury in the baseline state. Then after 17 minutes of this two-pulse protocol with stimulation, you can see how in the facilitatory at 10 minutes, these are average of 20 repetitions. At 10 minutes, there is an increase in the signal that was coming before from the brain. And this increase lasts up to 30 minutes. And in some of our protocols, we have monitored up to 80 minutes. And we have seen that these increments remain up to 80 minutes. That depends on many other circumstances, but I'll come to that later. In the spinal cord injury case, this was the fascinating part because we also see increase. Now, the signal in between, as I mentioned before, the comparison of the signal, the original baseline signal in between a spinal cord injury subject with a normal subject, is that there is a delay in the latency and also a decrease in the amplitude. But as you can see, after facilitating with the protocol, there is a powerful effect, both at 10 and 30 minutes. This is group data collected in this study, and published in 2012. In the group data, we're comparing the neutral state versus the facilitatory state. And as you can see, at 0, 10, 20, and 30 minutes, there is a significant response and difference in between those which received the stimulation versus with the right pairing of the pulses versus those which receive a stimulation with the wrong timing. That is for control subjects, and this is the graph for a spinal cord injury where the same effect was noted. In the next slide, I'm showing the inhibitory protocol. In the inhibitory protocol, we have the contrary effect. So this is the baseline trace with this amplitude and latency in the control subject. And as you can see, after 10 minutes, the signal that is coming through the brain is decreased. And this inhibitory effect remains up to 30 minutes in both the control case and the spinal cord injury subject. This is very important because it helps you to define that the other timing is actually working. Then we have the control group, and as you can see, this is the baseline established with the neutral protocol at 5 milliseconds intervals. And this is the result of the 1.5 millisecond interval. And as you can see, the signal is inhibited, so it's below 100% baseline in the control case and also in the spinal cord injury case, up to 30 minutes. Okay, so now motor evoked potentials elicited by cortical and subcortical stimulation follow the same pattern. By subcortical stimulation, we refer to a different technique. Now we're not stimulating in the cortex using the coil, the electromagnetic field. This technique is a little bit older too. It is a cervicomedullary junction stimulation. To do this technique, Taylor and Gandibia reported in early 90s that if you put two electrodes in the mastoid process behind the ears, one the anode and another one the cathode, and you run current through the two electrodes, you can excite the corticospinal tract at the level of the medulla. And this excitation of the corticospinal tract now is independent from the motor cortex. So it's a very good control test to tell the difference and to make sure that the changes that you're observing are at the cortical level or at the subcortical level. Because we know that since we are stimulating the whole system, the effect can happen up here in the cortex, in the neurons that are up there, or in these neurons. So this kind of tests allow us to know at least if we eliminate this part, if we still have the effect. And the results are that at the baseline, we have a facilitatory effect with the first protocol and an inhibitory effect with the second protocol in both people with a spinal cord injury and in control subjects. Okay, so we have established that the changes happen at the cervical level too. And then we are looking for potentiation of the motor output. So here you can see the baseline traces in the upper part for the STDP facilitatory. Now we are using the one that we know it works and facilitates the conduction of the signal. And we are showing the difference in between the baseline and after stimulation. And here we have a functional test. So this is mean area under the curve, comparing percentage of baseline, and you can see how the group that receives the facilitatory protocol enhances the change. And this effect is also seen or reflects also in a functional level. So when these subjects were exposed to the 9-hole peg test, which is a test using humans to establish dexterity, The purpose of the test is in this little board, they have 9 pins that are allocated in the reservoir. And the person has to hold the pins just doing a pinch in between the index finger and the thumb. And they have to transport the pin from the reservoir to 9 holes allocated in the other side of the board. And we time how much it takes them to move all the pins and put them correctly. And there is a training effect. So they improve just by doing this. The first times they're very slow and the pins fall from their hands. But after the training effect, they become better. And then after that, we test them with these protocols, and the results are shown here, up to 30 minutes. All subjects within this series were doing much faster than those when they received the protocol, the control protocol. Okay, so this is a video that I wanted to show you. This video is a patient that came to Miami. She's from Brazil. Probably some of you know her. Her name is Mara. She came to the Miami project after several years of her injury, and we exposed her to this Timingdependent plasticity protocol, just as I described it to you. She has a high cervical injury with very poor control on her hands, but she had some arm function control. And you can run the video now, please. Mara had been paralyzed for several years, and she had tried training techniques alone. When she came to us, she already had done these rehabilitation techniques, but we need the protocol. Here you can see the coil. That is how the coil clicks, and this is the response that it evokes in the arm in this case. With her, we focalize stimulation to reach biceps and triceps mainly, and this is her training hard. She will train every day after the stimulation session. And after several sessions, she started showing improvement. As you can see, the improvements are modest. There are not huge changes. The subjects are not moving their hands after this kind of a stimulation. But we know that they are enhancing whatever they have spared, and it helps people with spinal cord injury to regain any kind of function, which is very important for them. It changes their lives and their lifestyle and their dependence on other people. So in the next case, this is a different study. A couple of years after the first publication, Mike Irving, another postdoc in Dr. Perez's lab, started working with the same concept, but now they were trying to target the legs with the time-dependent plasticity. And for the lower limb, we do basically the same. We estimate the time that it takes to reach from the cortex to the legs. We estimate the time that it takes to reach from the lumbar spinal cord to the legs. And we do exactly the same kind of protocol. Now, because the motor cortex in the human that control the legs, it's more medial and not as exposed as the cortex that controls the hands, there were small changes and adaptations that we needed to do. It requires a stronger coil in the middle of the head, and the timing that it takes to reach the stimulation to spinal cord is a little bit longer. And the reports were very similar to the results that I just showed you. So instead of showing you again the results, I will show you in the next video another participant that came from Italy. Her name is Brunella. Brunella also had spinal cord injury. This case is different. Her case was not traumatic. You will see her just in a minute. And the important thing, or the important difference comparing this protocol to the previous one that you just see in the results, is that in her case we monitor up to 80 minutes and the effect remained up to that point. So this is her. Let's wait for the video just for 1 minute. Of course, the kind of training is different. She now is in a 0G in this kind of protocol. The 0G is a device that holds partially the weight. This is the special chairs that we have in our laboratory, where we can have a very good control of the position of the coil. We have a neuro navigation system that allows us to allocate with precision the coil. This is her again training. She will go for 90 minutes in training after the stimulation, as you saw. Again, the 0G, removing partial weight support. And at the end of the stimulation, she was very happy because she was able to, using the balance is still compromised, but using a walker, she was able to walk much longer. And then she was so excited about changes that she found after the stimulation that back in Italy, she sent us videos of her going upstairs. She had regained a lot of strength in her legs. These changes were not possible without this kind of stimulation. She had been training before without reaching the same results. Okay, now I'm switching to a different kind of modulation. I'll go a little bit faster now because this data is preliminary. This kind of stimulation is different to the one I just explained to you. In this case, we are using electrical stimulation that goes directly into the cervical level. This comes from previous studies done in California by another group. Dr. Reggie Edgerton and Yuri Gerasimenko have been working for years on the modulation of the central pattern generator at the cervical and lumbar levels. Mainly in animal models, but in the recent years they started doing it with epidural electrodes in the spinal cord of people with spinal cord injury. And they had a very interesting case published in Lancet journal in 2011 with their lead investigator there was Susie Harkema, a neurosurgeon in Louisville, that implanted the epidural electrode at the lumbar level, and after stimulation and training over a year, the person with the spinal cord injury, which was classified as HIA, was able to recover functionality of his leg and control, which was not possible before. But this control happened only under the stimulation. And so they came up with the idea of this kind of stimulator. This is a stimulator that allows you the same kind of current, but it goes through the skin, so you don't have to do surgery to implant the epidural stimulator. And we tried this recently. We're applying for a grant to do further studies using this technology. The advantage of this kind of a stimulation, and the difference with any other kind of a stimulator that you can find in the market, is that this stimulator can reach very high frequencies. So the idea of this current, which is so-called the Russian current, is to have a very high frequency biphasic kind of current grouped in blocks. And the frequency goes up to 10,000 hertz. And then the block's frequency goes from 5 hertz to 30 hertz. And when you put this on the skin, the very first sensation that you will have is like needles going through the skin. It's painful and discomfortable, but the discomfort lasts just for some seconds because this high intensity numbs the pain receptors. and therefore people can tolerate much better this kind of stimulation. So here we have a new kind of a strategy to train people using something called the Raphael globe, where they do kind of a game. The globe goes in your hand, and these are results that we preliminarily obtain with both the 9-hole pegboard using this stimulation at the cervical level. We observe that when they receive the stimulation for 10 minutes, there are already changes after a single session in both the speed that they do the board and also the strength during a pinch force. We also found changes in the motorable potentials that match the results with the right kind of stimulation. And also they were able to produce more force that we monitor in the EMG. We were very happy about these results because they happened just after a single session. We haven't run yet protocols where we train the person for several days or for several sessions. Now, the two videos that are coming are very short. One of them is this robotic training. You can start it now, please. This is the keen arm. The keen arm was developed for a stroke, and we adapted it for spinal cord injury. And what it does, it removes weight from the arms of the person in training. And it has several sequences where the person or the patient can learn how to move. In this case, this is one of our participants. He is playing a game, learning how to move his arms in the robotic system. And the virtue of this system is that it allows fine measurements of the arm movement while the person is executing the movement. And you can do a lot of different measurements with this kind of technology. We in the Miami project are one of the 3 or 4 centers in the whole country in the United States that have this kind of technology. And there are several publications that we've done using the keen robotic arm. Okay, let me just wrap up to the next. This last video is something that we've been working lately. It's also a training technique. You can run the video for me, please. Okay, so this is Juan. This is very recent. This is one of our collaborators. What he's doing here is using sensors that are located in his arms. The sensors can establish the position of the arm in space. And at the same time, he's wearing electromyographic electrodes, surface electrodes in his arms. So we can monitor the movement that he's doing and have an accurate idea of what is happening in each muscle of his arm. As you can see, he has to do several different kind of movements to match the position of this sphere in the screen. And we've been doing this kind of rehabilitation with patients with spinal cord injury. It's a very powerful tool to train people. Now let me, okay, so I'm close to the ending. This is the team I work with. This is Dr. Monica Perez, the principal investigator in our laboratory. These are my colleagues. They come from all over the world. We do speak every language possible. I would like to thank the founding institutions.